Hi everyone, this is Advanced Concepts Presentation 5. We're going to focus on the production of ATP through cellular respiration. So we're going to mainly focus on aerobic respiration with the use of oxygen, but we're briefly going to touch on the basis of anaerobic respiration without the use of oxygen. So the description: cellular respiration is the process that allows your body to harvest a huge amount of energy from a single glucose molecule, and it's so efficient that we get 30 ATP for every glucose molecule that we consume. We're going to break down where all that ATP will come from in this process, and for this presentation we're going to mainly focus on how we generate ATP, NADH, FADH2. Then we're going to go through the name structures and enzymes that are involved in each of these steps. From there, we're going to convert the rates of NADH, FADH2 in order to form ATP, and we're going to calculate exactly how we're going to form that 30 ATP in this process. And then also we're going to touch base on what steps which are going to be used for an ATP that's going to count against our total formation. So the rules: one NADH will form 2.5 ATP, one FAD will form 1.5 ATP, and then ADP plus a phosphorus will give us 1 ATP. So shuttling the NADH and the FAD, they won't directly generate ATP, but moving them with the hydrogens and electrons that they collect through the processes of glycolysis and Krebs cycle will form a gradient down electron transport chain. We'll shuttle them through the enzyme ATP synthase, and that's where they will generate ATP later on. So what is cellular respiration in the first place? It's the combustion of fuels into CO2 and H2O in order to create ATP. And aerobic, it's an aerobic process, meaning that it involves the use of oxygen. And Krebs cycle and ETC in the mitochondria are heavily used in order to produce ATP later on in this process. So there's two types of respiration. There's aerobic respiration, which we're mainly going to focus on, which will take glucose, phosphorylate it in glycolysis. Then we're going to form pyruvate. We're going to move it over to the mitochondria, where we'll use it. Aerobic respiration is with oxygen, so aerobic respiration will go through the Krebs cycle and then electron transport chain. And then to the other side, we can take glucose and form pyruvate, and then we can move it through anaerobic respiration without oxygen, which will go through fermentation and either form lactic acid or alcohol and carbon dioxide. So those are the two processes that we can use glucose. So focusing mainly on aerobic respiration with oxygen, we'll go through glycolysis. So glucose molecule will come in through the regulatory step, hexokinase. We'll have to phosphorylate it in order to trap that glucose molecule in the process. So we have to use 1 ATP in order to add a phosphate group, which will form glucose 6-phosphate. And then the second regulatory step, phosphoglucose isomerase. And then we'll form fructose 6-phosphate. We'll have to use another ATP in the process of phosphofructose kinase. Then we get fructose 1,6-biphosphate. And then through fructose biphosphate aldose, we'll get dehydroxyacetone phosphate. Then triose phosphate isomerase will turn it into glyceraldehyde 3-phosphate. Glyceraldehyde 3-phosphate dehydrogenase will take an NAD and a phosphorus. We're going to reduce it and form an NADH and a free hydrogen. And then we'll get 1,3-biphosphoglycerate. And then phosphoglycerate kinase is going to take an ADP and then form ATP. And we'll get 3 phosphoglycerates. Then phosphoglycerate mutase is going to form it into 2-phosphoglycerate, go through enolase, so H2O will come off, and then we're going to form phosphophenylpyruvate, PEP. Then through an ADP, we're going to form an ATP through pyruvate kinase and get pyruvate as our end product. So all in all, glycolysis, we have to get we have to use 2 ATP right off the bat. We're going to form 2 NADH, which will later give us 3 ATP in the electron transport chain. We form 2 ATP here, and then another ATP. So we get 4 ATP, but our net product is 5 ATP from this process. And then briefly touching on anaerobic respiration without the use of oxygen. So we'll only get 2 ATP from glycolysis in the cytoplasm through this form. This is because we take glucose, we only get that 2 ATP formed from it. We get 2 pyruvate, which will convert to lactate, and then NAD is going to regenerate and keep this process going. So it's a very poor way of producing ATP compared to aerobic respiration, but it is a way of getting ATP without oxygen present, so it's definitely needed. So back to aerobic respiration and converting a pyruvate. So pyruvate has to form into acetyl-CoA, and this process will generate 2 NADH, and so that will give us 5 ATP later on through the electron transport chain. So moving that acetyl-CoA into the Krebs cycle, we're going to crank it out, and then going on to isocitrate, moving through isocitrate dehydrogenase. We're going to get a little bit of ATP from there, and then moving on, we're going to go through alpha ketoglutarate, and then the alpha ketoglutarate dehydrogenase complex. We're going to get 3 ATP, so we're going to move NAD. We're going to reduce it to NADH and a free hydrogen. And then keep moving on. We're going to go through succinyl-CoA. And succinyl-CoA synthetase is going to take ADP and a phosphorus. It's going to reduce it into GTP or ATP. And we're getting ATP from that. And then succinate, we're going to go through succinate dehydrogenase. We're going to take FAD and form FADH2. And then moving on to malate. We'll go through malate dehydrogenase, where we take NAD. It's going to be reduced into NADH and a hydrogen. So all in all, we get 2 ATP. We'll get 6 NADH, which will later on give us 15 ATP through the electron transport chain, as well as 2 FADH2, which will later on give us 3 ATP. So shuttling all that into the electron transport chain and then oxidative phosphorylation. So moving that 2 NADH originally from glycolysis, we're going to form 3 ATP. Then the 2 NADH from pyruvate will give us 5 ATP. 2 FADH2 from the Krebs cycle is going to give us 3 ATP. And the 6 NADH from the Krebs cycle is going to give us 15 ATP. So how this is done is we're going to set up a concentration gradient using these proteins. So the enzymes, they're going to push the hydrogens out on this side while moving the electrons, the negatively charged electrons, down this way. So we're going to have positive charge out here with the hydrogens, negative charge with the electrons in here. And so these two definitely want to come back to each other to form an equilibrium. So the only way we can do that is by shuttling through the ATP synthase. So we're going to have a concentration gradient. These hydrogens are going to come in through here. They're going to force through, and that concentration gradient is going to generate free energy, which will be able to take a lot of ATP and a phosphorus and form it into ATP. So that's where we get a ton of ATP through this process. So just to recap, glycolysis will give us 2 ATP right off the bat. It'll form 2 NADH, which will shuttle down to electron transport chain. And the Krebs cycle will give us 2 ATP off the bat. It also gives 6 NADH and 2 FADH2, which will move on to the electron transport chain. And then ETC through phosphorylated oxidation, we're going to get 26 ATP. So for all in all, we're going to have a total net gain of 30 ATP for one glucose molecule. So here are my sources. Just let me know if you have any questions, and thank you.